This tutorial is an introduction to number systems that help drive both our mathematical world, including finance, as well as the digital world that our computers use as their most basic building blocks. This video will focus on understanding the decimal and binary systems, while later clips will focus on the octal and hexadecimal, with a final clip bringing it together demonstrating the use of these number systems in modern computing. Our decimal number system is the one we know and use every day. At its most simple level, it starts with 10 different digits. Just like a decade means 10 years, the decimal means 10 digits. This includes the numbers 0 to 9. If you can remember back to the early years of primary school maths, you might have used single blocks to represent a 1. A grouper box could be put onto a piece of paper with a column for ones. The most ones that you could fit into a single column is 9. If you have just the one extra block, it doesn't fit. And the solution is to add a tens column and put the 1 in there. When the tens column gets to 9 and we want to add one more, we add an extra column to the left and place a 1 in it. That process continues for each column as it gets full. It's important to remember the empty columns are not just blank, but there are zeros in them. Those zeros have meaning because it holds a place and tell us what the other columns are worth. When we think about the number 687, it really means we have 6 lots of 100, plus 8 lots of 10, plus 7 lots of 1. It's sometimes called expanded notation. We don't often use expanded notation in decimal, but understanding the concept will help when it comes to the other number systems. You'll notice in this example I've included a row which has 10 to the power of 0, 10 to the power of 1, 10 squared and 10 cubed. It's another way of recording the ones, tens, hundreds and thousands columns. So the key messages when it comes to decimal are we only use the numbers 0 to 9 to represent all numbers. When a column is full and you need to add one more, you add a column to the left. This number system is also known as base 10. So let's move on. The binary number system is very similar to decimal with only one key difference. Instead of the numbers 0 to 9, there are just two digits, 0 and 1. Once again, we start with the ones column, but because we only have the numbers 0 and 1 to work with, when we put a 1 in the column, it's now full. If I want to add a second 1, using the same principle as before, if the column is full, we need to add 1 to the left. The big difference is that the column is not called tens, but think of it more as twos. Using this example, we have a 1 in the twos column and a 0 in the ones column. So the number 10 in binary is the same as 2 in decimal. In this example, 101 in binary could be written in expanded notation as 1 lot of 4, 0 lots of 2, and 1 lot of 1. In other words, 101 in binary is the same as the number 5 in decimal. As we add more columns to the left, it looks intimidating, but if you keep the same principles, it makes some sense. Take a moment and work out in your head what the number 1011 in binary is equal to in decimal. The process that you should have used was we've got 1 lot of 8 plus 1 lot of 2 plus 1 lot of 1. When you add them together, we get 11. So the number 1011 in binary is equal to 11 in decimal. When we keep adding a few columns, the numbers look bigger and perhaps intimidating, but the process doesn't change. This one's pretty easy. It's simply 1 lot of 128 plus 1 lot of 1. So this really big number is the same as 129 in decimal. To convert from decimal to binary, start by drawing up the table that we've been using. We work from left to right, and wherever we can we take away the column heading from our number. Starting from the left in this example, where we are trying to convert 28, we cannot take away 128 without going into negatives, so we leave it blank or write a 0. Again, 64 cannot be taken away from 28, so it's blank. 32 is the same. However, we can subtract 16 from 28, so we record a 1 in the column, meaning this number includes one lot of 16, and we now have 12 remaining. We can take 8 away from 12, so again we record a 1 in the column and we're left with 4. We can also take away 4 from 4, so we record a 1 and have 0 remaining. For the remaining columns we can't take away 2 or 1 from 0, so both of these columns record a 0, meaning the number 28 in decimal is the same as 11100 in binary. You'll notice that I haven't recorded the zeros to the left because just like in decimal, leading zeros don't mean anything. But the zeros to the right are significant as they're placeholders, so they must be shown. When we're working in binary, the numbers 0 and 1 are used. When a column's full and you need to add one more, add 1 to the left. It's also known as base 2. Try the following conversions now, using a paper and pen. Here's the table that will help you with the working out. Press pause so you've got time to work out the answers, but the 4 questions are: the number 11001 in binary, what is that in decimal? The decimal number 61, what does that look like in binary code? The third question, 101011, what's its value in the decimal number system? And finally, convert the number 198 in decimal to a binary number. And so here come some answers. That brings us to the conclusion of this particular clip. In the next video, we'll take a look at the octal and hexadecimal number systems before moving on to the practical application in computing. See you then.